Hello my friends and welcome to this fifth video of the series Consciousness as a Modular Phenomenon. In the previous section, in the previous video, we got to the conclusion that we wanted to talk about partitions in a more topological point of view, as the language that we are going to use for talk about consciousness, because one of the principles I want to base all these ideas is that consciousness is partitioning, and partitioning of some kinds is consciousness too. So in addition, we want to add this new kind of additional language to quantum mechanics to be able to explore further the topic. So in this section, we'll advance toward the goal of finding this new mathematical language that we want to add to quantum mechanics to be able to extract more information, and we are going to do that through an intermediary step. We are going to do a kind of stepping stone in physics to be able to find out which is this language that this way of speaking about partitions that is more suitable for us. We already saw in the past video that we wanted to go in the direction of fiber bundles, because fiber bundles encapsulate this tower of states, massive tower of states, equivalent classes, which we project on a certain space or state, which is kind of the superposition of all this tower of states. And this is very reminiscent to the parallel processing process that we know that is happening in our consciousness. In mathematics, one of the ways to represent partitions in a more geometrical way is the idea of fiber bundles, which is more coming from topology, but in geometry we also can represent fiber bundles. Let's see a physical analogy of these ideas in quantum mechanics. We need a toy model to do that, and that is closer to the quantum world, and that will allow us to kind of put some images in our head, let's say, about the conscious phenomena. And I propose to talk about the so-called quantum revivals. Quantum revivals are a very useful laboratory for simulating something that has massive superposition of very chaotic states, and phase locking also, which are some of the properties that we saw that are desirable, let's say, for simulating conscious processes. And also robust, let's say, superposition of the states. So let's suppose that we are, let's describe first what is a quantum revival. Quantum revival is when you have, for example, let's fix an idea. Suppose that you are in a cage, in a very small cage, a molecular level cage. You have an atom inside or a particle inside. And this particle is bouncing in between the walls of this cage, molecular cage, and you want to describe the motion of this particle quantum mechanically. So we know from experiments even, and also from when you solve the Schrödinger equation for such a system, that the system will behave, you represent this atom in the middle by a wave packet, for example, yeah, it's a particle, let's say, an ideal particle, let's say, not an atom, but a particle, let's say, you can represent it by a wave packet. And the initial conditions are given by the boundaries, let's say, of that it has, this cage. And then the atom is bouncing between one wall and the other. But what happens quantum mechanically is that the wave packet, when crashes with one the wall, it gets completely destroyed. Kind of this is dispersed in all the cage. And of course, with the conditions that has zero probability to be very near to the walls of the cage, but in the middle it happens a lot of chaotic motion of the several states that compose the wave packet. And what happens is that after some time of bouncing chaotically, the wave packet appears once again, sometimes in the same position where it was at the beginning, sometimes in the middle of the cage, sometimes close to the wall, but kind of the packet, it gets kind of revived. It revives, exactly, that's what the name, after some bouncing. And especially, for example, if you have one of the walls moving, I mean, imparting some momentum to the particle, so you get a very precise description of when those revivals will occur in this motion. So, but this is one example of revivals. In reality, what happens, I mean, the general solution of the Schrödinger equation, you can calculate that any system, the wave function of any system will always have a revival at a long time or short time, depending on the scale where you are calculated. But the very nature of the quantum mechanical, let's say, calculation, the evolution described by the Schrödinger equation, it has always revivals. This is one astounding property because, for example, you can say if there is revival, that means that there is not such a thing as chaos really in quantum mechanics. And in reality, quantum mechanics kills chaos, if you want. But this is for small systems, very small systems, very quantum systems in the very quantum limit. Once that you start adding, for example, describing the wave packet with more states, and you get, for example, a system that has larger mass, what you notice is that magically, let's say, the description, the evolution described by the Schrödinger equation, it's matching the classical one. I mean, for some period, and then it revives. It has a revival to the initial quantum state, but then starts once again following the kind of the classical path, what you will expect from the classical path, and then it revives again. And this revival time, it gets longer and longer as the system gets larger and larger, and as the number of states that you use for building this wave packet or whatever you are using for describing the system, the base you are using for describing the quantum mechanical system, as it gets larger, for you describe it more precisely, and the mass of the particle or the system gets larger, so this time of revival gets very long. That's more or less what one expects in the classical system. So for a long period of time, still in the classical limit, you are going to have chaos, you are going to have all the classical behaviors. But if you go to a very quantum-like system, or a quantum system coupled to a classical one, then you can expect to have revivals. And these kind of phenomena have been detected in many areas of physics and in quantum physics. So it is experimentally, it has been confirmed. The system itself, the system of this particle, of this wave packet, you can say that exists only in the moment of the revival. So the robustness of the system, it comes from the fact that this superposition is chaotic most of the time, but in some moment there is a kind of phase locking mechanism, because it's exactly what is happening when you do the calculation of the revivals. Is exactly what is happening. It's a mechanism of phase locking between the several states that are bouncing chaotically, and in one moment the phase locking of the quantum mechanical phases of those states, they kind of play together, so the state of the whole wave packet gets revived. So you have together in one toy model, in one quantum mechanical system where you can play a lot with that. You have all these properties of a very massive tower of states that are superposed, a very robust rebuilding of the initial state. You have also this phase locking mechanism at play. And so it is an ideal laboratory for what we want to do with our with the properties of the consciousness. Because if you remember, this robustness was one of the observable properties of consciousness. This phase locking mechanism was there. This chaotic behavior was there. This massive superposition of states. Of, in the case of consciousness, we say that there were partitions of the observed system. This massive superposition is also there. So we have an ideal kind of toy model to play in quantum mechanics with those revivals, to kind of extract by analogy some kind of lessons from that. So one interesting thing about these revivals is when you try to solve the Schrödinger equation for such, for example, wave packet, no? Naturally, number theory enters in the game because of two things. Because you have, usually you use a finite number of base states to model the wave packet. So you have natural numbers entering there, and you have the superposition mechanism that is kind of a summation. It's a kind of superposition. Is at the end of the day is a sum of some packets or probabilities. So this sum is what makes to enter number theory into this phase locking mechanism, because the phase locking mechanism has something to do with the relationship between the quantum numbers of those base states, and those are natural numbers usually. And so all this game at the end of the day, it's play at a level of number theory. This phase locking mechanism is a kind of play between natural numbers, and the relationship between some ratios of numbers, it is very interesting there. You get revivals only when there is a kind of relationship between the quantum numbers of the states in the web packet. So you can even calculate when this revival will occur, the time of revivals. And so all this has to do with the number theoretical properties of those natural numbers that are entering there in the game. And the superposition is the sum. So there enters the arithmetic and all the story of number theory. So, but then when you do you go to the classical limit, and the natural numbers that you're adding become large, and the mass of the system becomes large. This kind of relationship, the revivals themselves, they become very spaced in time. So you kind of get this information kind of disappears from the behavior of the system, at least for a long time, and then you get the revival, but it disappears. And it's kind of reminiscent of the behavior of our consciousness, because we don't really feel any structure in this robust, let's say, thing that we call consciousness. You just feel something continuously going in time, that this scene that we are observing, for example, in the case of, we were discussing last video, it's kind of robust, is stable, is kind of smooth transition in time, from point to point in time, let's say. So there is no kind of a structure on that, obvious structure at least, And it's reminiscent of the kind of robustness that you get in the wave packets in this toy model, because in the toy model, in reality, there is a lot of things going on quantum mechanically to get this phase locking so precisely, to get to the classical motion of the particle of the wave packets. And in reality, there is a lot of phase locking going on. I mean, it's kind of magical, kind of a lot of things going on. Only that if you were, for example, the wave packet, imagine that you were this wave packet, you wouldn't feel anything. I mean, you wouldn't feel any structure at all. I mean, you just exist in the moment that there is a revival. And this is interesting thing that I would like to use as an analogy. I would like, let's say, to propose the analogy that this existence of these wave packets in a revival is kind of reminiscent of the robustness in our consciousness. We may perceive a conscious, I mean, a very robust, a very without structure experience at a conscious level only because we are like this wave packet. We are conscious only in the moment of this revival. I mean, I want to use this analogy between this toy model, let's say, of the revivals and our consciousness. Suppose that you are like this wave packet, and you are conscious only in the moment of the revival. So you will experience a very classical, a very smooth, a very peaceful, let's say, evolution, and almost classical, without any chaoticity. I mean, the chaoticity, classical chaoticity, but nothing. You don't feel nothing about these base states that are kind of phase locking there. But this phase locking is what is generating your experience in reality, because the wave locking mechanism is what's generating your experience. So this is a bit reminiscent of the mechanism in consciousness. So the superposition of a tower of states and with this phase locking mechanism, kind of the phase locking mechanism, you can kind of consider it as the generator of the equivalence classes that you are projecting in the fiber. An equivalence class will be one of those set of base states that has a phase lock in such a way that they project vertically into the wave packet. Kind of, they give the wave packets once again. You can have a lot of different states that are not really, with the phases of these states, base states are not really locked in such a way, or they don't compose, they don't sum up in such a way that they reproduce the wave packet. So they reproduce the chaotic states, let's say, that you have when the wave packet, for example, crashes into one of the walls. Fiber bundles are indeed equivalence classes inside the whole set of Hilbert space of the system. So they allow, I mean, these fiber bundles, they allow, and these equivalent classes allow us to do a partition of this Hilbert space into fibers that they project vertically to a unique wave packet. So using this geometrical representation of the reconstruction of this wave packet, the revival of the wave packet, we can see that these fibers, this vertical projection, is a kind of visualization of the process of revival of the wave packet. But now suppose that we made this analogy with our consciousness, no? Because we say that if the revivals are a good laboratory for those properties of our consciousness, then we can consider that this geometrical representation, this projection by fibers into a base space that is a kind of sum of all these tower states is maybe also a good representation for some kind of visualization or process that is going on at the level of our consciousness. And so that's what I say, that talking about consciousness with the language of partitions, it allows you to immediately go beyond all what we were saying before, because it gives us a new language, a new toolbox to play with these kind of projections of spaces, with these towers of equivalent classes that we didn't have before. I mean, we got to that just by introducing this new language and by considering that partitions were involved somehow in the game, in consciousness. So so maybe these fiber bundles are also, like I say, a good geometrical language for describing the process of formation of our conscious states as a massive superposition of equivalent partitions of a system. What this equivalence means, we will make it more kind of precise later, because by now, for example, in the case of the quantum revivals, we saw that the equivalence is this phase locking mechanism that when they sum up, it gives once again the same, all these phases kind of cancel each other, and you get the wave packet revived once again. So this is kind of the equivalence classes in the case of the fiber bundles for these revivals. What is the same mechanism or the same ideas in the case of the analog system of our consciousness? This still, we don't have an idea about that, but we want to advance using this analogy. We want to advance to extract some information in this direction. So at least we are going to use this kind of vertical projection of this tower of states into a base space as a kind of visualization. We will see that this is more than a visualization. I mean, this is kind of a very, very useful kind of way of thinking about consciousness, and will allow us to make a lot of progress. So this is the first step in the language, in the change of mathematical language that I want to do. And this language of fibers, this kind of diagrammatic representation, this kind of graphical representation, visualization of this vertical projection into a base space, this is something that we will meet in many other areas of mathematics. And in fact, this visualization, this superposition of equivalence classes or fibers, is just a stepping stone for us to get to this other language that we want to find. So let's go from the geometrical representation, of fiber bundles to a more topological representation of fiber bundles. Let's talk more from the topological point of view about fiber bundles. Not much about a vertical projection as a kind of line or something like that. That is not really the case in general. In mathematics, what you are doing is mapping reality of classes of equivalence into a kind of a coset of the base space. So in reality, this language will allow us to make contacts with other areas of mathematics also. But then let's go to this other area of mathematics, that is topology. So the fiber bundle diagram, this graphical description that we made for this projection, that I remind you, we are always talking about partitions in reality, because like I told you, partitions are equivalent classes are partitions. Like I say, if you want to partition, for example, the Hilbert space, in the case of these revivals, what you do is to generate equivalence classes according to this property of the revival, let's say. So this is a kind of partition. So whenever you have equivalence classes, you are partitioning the system somehow, a space or a set. So let's talk about the topological structure that comes with this kind of fiber bundles diagrams, like we saw, this graphical description. The vertical fiber projection is a map, like I say, in reality. Let's call the map pi, just because we are going to use the same diagram time and time again. From now on, you will see appearing the same terminology and the same letters even. I want to use the same diagram always, just to remind you that the origin is this that we are discussing now. So topologically, this fiber, this projection is a map between a space X at the top, the space let's go to an analogy in the conscious. Let's call it the space of all the partitions of a system we are conscious, that we are being conscious of. So X will be the space of all the partitions we are kind of doing in the system that we are observing, let's say. This landscape, for example. No? So in this map pi, this fiber map into pi from X goes to a space that we will call Y, and this is the space where is the sum or the kind of parallel superposition of all these equivalence classes. So Y is the space of the revivals, if you want. Is the space of the superposition of all this space X through the map pi. And the map pi is a map of it's a summation, it's a sum over the classes, equivalence classes. Equivalence classes of some kind. Like we saw in the case of the quantum revivals, it was equivalence classes of related to this phase locking mechanism. We will see what is the equivalence classes in the case of the consciousness spaces that we are talking about. These states of conscious states. So, like I say, we are playing, I know, a little bit, not rigorously, but it is a kind of toy model, a stepping stone towards the language that we want to reach. So, let's say that the point where the fiber meets the space, the sum of all these tower of states, we'll call it y hat, small y hat. So this terminology will go with us until the end of the video. So let's discuss it now. So the space y, the base space where we are projecting, this represents the states of consciousness, the conscious states. This is the sum of all these partitions that we are doing. So the space y is the space of the points. Each point in this space is one kind of conscious state. And then, for example, y, one point in this plane or space Y can be my view of a landscape, for example. But the space X contains all the partitions that I am doing for this landscape. And the projections are exactly the equivalence classes that we are going to discuss later, how to form them. But you see the analogy, more or less. I want to say that these projections, these partitions, the way that I sum it is through equivalence classes of some kind. And my conscious experience is what is kind of described in the base space, where I am projecting all this tower of equivalence classes. So pi being a vertical map, that means a vertical map of equivalence classes, it is necessarily, mathematically, it is a homeomorphism between those two spaces. It's a homeomorphism between those two spaces. That means that it is a group homeomorphism for the fundamental group of those two spaces. And now a little bit of topology. The fundamental group of a space is the set of operations that preserve the topological structure of loops in that space. That means if you have loops, for example, in the space, and you consider all the operations that preserve the fundamental, let's say, operations between those loops, you have what is called a group homomorphism. For this kind of group, the fundamental group, that is a topological group, let's say, in a space. So this pi, this projection, is a group homomorphism for this fundamental group in both spaces. So like I say, the fundamental group is a set of operations in each one of those spaces that preserve the topological loop structure in each space. So the map pi between X and Y preserves the composition of the fundamental group operation between both spaces. Loops in X, that means arcs that are connecting points in the same fiber, are mapped into loops in the base space. So if you have, for example, in the fiber, you connect with arcs, some points in the fiber, different points, and you project those arcs, they kind of get collapsed into loops in the base space. This is more or less for visualizing what does it mean, this map. So this is the meaning of that this pi is kind of preserving the loop structure. That's why, because for example, arcs in the fiber, let's say, are kind of loops into this X space, and the loops that result from the projection of those arcs are loops into the base space, the projected space. So that's more or less how to visualize that this pi, it kind of map the loops information in the higher space into the base space. Let's call X just for the higher space, or the space of partitions, let's say. So this, I made emphasis in all this description because it will be with us for a long time. I mean, we are going to see the same kind of diagram in the same kind of machinery of projections, or speaking about topology of those spaces along all these videos. So this is the most important thing, that is when this is what we gain when we start speaking about partitions, because partitions bring the language automatically of equivalence classes. The equivalence classes bring the language of fiber bundles, and the fiber bundles bring all these very rich topological structures that are in the background, and it brings something very important: a group that is there because we are using fiber bundles, because we are using these projections, this summation. This group is this fundamental group I was speaking about, and it's a group that comes by default. I mean, we have it already there just because we are talking about this kind of diagrammatic representation of this projection. It will be very fundamental for many things that we are going to describe later, because those groups, when you have groups, immediately you will have certain things by default, which comes from group theory. When you have a group, you can consider all the machinery of group theory, and one of the things that comes in the box of group theory, the three seal of theorems will allow us to make contact with number theory and with modular mathematics, p-adic mathematics specifically. So that's the plan. The plan is to start speaking about those partitions using all this topological machinery. And with the topological machinery, we gain a group. We introduce a group in the discussion. The fundamental group comes there. And the fundamental groups will lead us naturally, because it's something that is coming it's nothing new. I mean, in mathematics, when you do group theory, you are immediately led to the seal of theorems, and the seal of theorems are a connection with number theory, and specifically with modular mathematics, with p-adic numbers. So that's the plan. That's the path that we want to follow to this. At the end, this will come at the very end of our videos, but now we are going I want to explain why I am following this path of topology, let's say, because this will lead us in a very formal way, very rigorous way, in fact, towards our goal of introducing this new language of modular mathematics in the game of consciousness, of the topic of consciousness. When we assign a kind of conscious meaning to some of the elements of this topological diagram that we showed before, this projection diagram, we will assign consciousness meaning to some of those elements. We will be able to extract enormous amount of information about the connection between all those elements, and that's exactly what we want. If we say consciousness is partitioning, immediately we are falling in this diagram. The diagram is there for us. All the machinery of group theory is there for us to give us information, and if we assign consciousness meaning to some of those elements, like we did already, because we say that the space X, if we consider that this space is the space of all the conscious partitions that I'm doing when I have a conscious experience of a landscape of something that I am observing, if this is this space, and the space Y is the space of the summary, let's say the sum of those partitions, that is my real experience. I mean, I don't perceive these partitions as such. What I perceive is the sum of all those partitions, and this is my reality. This is the classical reality. This is the revival wave packet, and this is when I exist. My consciousness exists exactly in the point of the summation, this in the base space. But in the background, there is all this enormous machine of partitions that somehow I am summing through this vertical projection, this pi, and this is more or less the analogy that I want you to have in mind. We know a lot about structures in mathematics that have the same topological representation, the same kind of diagrammatic representation. Because it's the general abstraction, the general representation for any kind of superposition of states. Specifically, when you have these partitions, like I said, equivalence classes, these partitions and equivalence classes are the same thing. And when you have this structure, they come immediately. I mean, it's out of the box. Then, indeed, there is another very strong, very powerful area of mathematics that uses exactly the same topological representation. And I want to make emphasis, later I will put the two diagrams together showing this representation that we are using and the representation that is used in this other area. I will already say is this other area of mathematics that is also a way of speaking about partitions in some way, is the theory of Riemann surfaces in complex analysis. We are going to talk something about this theory, not too much, because the idea is not to introduce too many concepts, to go too deep into mathematics, but this theory of Riemann surfaces in complex analysis, it has exactly the same topological diagram at the base. You will see. This is the mathematical language. This is the mathematical language that we are going to use as most suitable for talking about partition. Why? You will see in a moment. I mean, Riemann surfaces in complex analysis will allow us to give meaning to certain properties of our consciousness that are encoded in this diagram. Exactly. That is exactly the same diagram but coming from a different perspective and more topologically. Exactly. So topology kind of isolate us from the geometrical point of view or from the Riemann surfaces point of view. Is kind of a more abstract point of view. So that's the richness of topology, that we can use this diagram in a geometric situation, like in the case of the wave packet revivals, and also in a more abstract situation in the Riemann surfaces theory. We will see that the power enormous that give us this to attack those partitions using the enormous power of Riemann surface theory and complex analysis is extraordinary. I mean, we are going to extract a lot of information about consciousness when we assign conscious meaning, let's say, to all those elements in this diagram. So in the following section, we are going to dive in that very well-known area of mathematics, that is Riemann surfaces and complex analysis. And we are going to use all that machinery, let's say, to extract information in the same way that we did in this video, kind of by analogy with a physical system, like in the case of wave packet revival. We are going to do more or less the same between the topic of consciousness and what is going on in the Riemann surfaces area. You will see that by assigning meaning to those elements of this diagram in the Riemann surface context, we are going to be able to extract enormous amount of information about the topic of consciousness. Same as we did in a moment ago, using the analogy with the wave packets. We were able to come to this diagram. Exactly this stepping stone of the wave packets, these revivals, allow us to come to this diagrammatic representation of the process of formation of a conscious experience. Okay, so we'll leave this video here, and in the next video we are going to talk about Riemann surfaces, the fundamental group, and the J function invariant. Thank you.